In this section, we're going to look at the role of momentum and impulse and forces when it comes to safety. We'll start with an example looking at boxing and boxing gloves. So let's suppose we have two cases here. We have a boxer who is taking a punch by someone wearing a boxing glove. And let's suppose at a later moment or a prior moment, there's a person who comes in and punches him with a bare fist. Now, we might agree that the mass of the hand with the glove and without the glove are approximately equal. Now, certainly the one with the glove will weigh a little bit more because of the weight of the gloves, but the weight of the gloves is very small in comparison to the hand. So in other words, then they have approximately the same momentum. And when the hand lands, whether it's with the glove or the plain fist, the momentum will be zero in both cases. So what we have is the changes of momentum. The changes in momentum are equal in both cases. Because they start out with the same momentum, they both end up with zero momentum, so the change in momentum for the glove and the bare hand are the same. So the change in momentum are the same. What is different about them is the time over which that occurs. The time over which that occurs. The rate of change of momentum is different. So in the case of the bare fist, the time that it takes for the fist to come to a stop is very small. It's a small delta t. It's a small delta t. Whereas with the glove, it is a longer delta t. So since the delta t is longer, we have a larger denominator, that means that the rate of change of momentum will be less. And for the bare fist, the rate of change of momentum will be greater. And the definition of the rate of change of momentum is the net force. The net force is the definition of the rate of change of momentum. So the rates of change of momentum will be different. That means the forces will be different. The forces will be very different. In the case of the bare fist, the force will be greater. And with the glove, the force will be less. And that happens because of a change in time. If, let's say, the fist comes to a rest in 0.01 seconds, and the glove comes to rest in 0.1 seconds, that means that the time is 10 times greater. And if the time is 10 times greater, the force will be 1/10 as great. So even small amounts of time, a change can make a huge difference in terms of the force that is felt. And it turns out this is the way that all padding, mats, knee pads, shoe padding, car interiors, and airbags are designed to do inside cars. What an airbag is designed to do is to increase the time that it takes to bring the velocity to zero, to increase the time for the momentum to change. And that is the role of all of these items. Car interiors, they are oftentimes padded. Although with the advent of airbags, they're not as padded as they used to be. So that's the role of this sort of thing. Well, let's take a look at jumping and falling. Let's suppose we have someone who is on a ledge, and they jump off that ledge, and they land stiff-legged. And another person jumps off, and when they land with soft knees. Which means as soon as their feet come into contact, they bend their legs, and they end up in a squatted position. Well, what happens in the gray case, the first case, the stiff-legged case, is that delta t is small. they come to an abrupt stop. But in the red case, what happens is the change in time increases. The delta t is larger. And so if we're talking about the same change in momentum in both cases, and we have a greater delta t, and in the stiff-legged case, we have a lesser delta t, well, then that means that the force will be larger. The rate of change of momentum is the force. The force will be larger in a stiff-legged case, and it will be less. The force will be less in the soft-kneed case. And this is the sort of thing that stunt people learn to do. You know, stunt men and women learn to do this. But here's what's interesting. If someone comes to a stop in, let's say, 0.01 seconds when they land stiff-legged, and someone really slows that down to, say, 0.5 seconds, that is 50 times greater time. And so if we increase that by 50 times, the force will be 50 times less. So it's all about decreasing that or increasing that amount of time, which brings about a much smaller force. So what do these graphs look like? We'll look at the momentum and the time. So at the instant before the stiff-legged one has an impact, it's got a high velocity, which means a large momentum, and then it comes to a stop. And so its momentum is 0. And that change in momentum occurs over a small delta t. Well, in the case of the soft-legged person, they extend that amount of time for their momentum to become 0. And so we can see their delta t is larger. Now, if we look at do an Oizerga on this, origin is 0, 0, y-axis is momentum, x-axis time. The intercept at t0, it's the initial momentum. What we can read is momentum and time off this graph, and the slope is delta p over delta t. Oh, the rate of change of momentum is the net force. So we can see in the red case, we have a smaller slope. That means a smaller force. And in the stiff-legged case, we have a greater slope, so we have a greater force, showing up as the slope in that graph. In our next installment, we are going to look at cars and their design and how that relates to changes in momentum.